Very good afternoon. We start our next set of three lectures on module 3, which is properties of a pure substance. In module 1, we looked at concepts and definitions. Module 2, we looked at what are the laws of thermodynamics and how we applied these two problems. We got to a point where we could take a system, show the system boundary, decide which equation to put and what assumptions to make. That gave us a relation between heat, work and properties for either a closed system or an open system. So now if we know any two of those, the third one can be calculated, and that becomes the starting point for analyzing any problem or looking at the performance of any real application. So that's what we will look at. Today we will visit what are the properties of a pure substance, what is a pure substance, and in particular we will look at thermodynamic properties of a pure substance. Okay, so we begin with by saying that properties of a pure substance could mean a lot of things. We could have physical properties like what you would have come across in solid mechanics or in strength of materials, things like elasticity, modulus, those types. Or there could be electrical properties, resistivity, like that. Chemical properties, that is reactivity. Transport properties that one comes across in fluid mechanics, main ones there being the viscosity. And then we have thermodynamic properties and also say magnetic properties. So all in all, a material, when you say what are the properties of a material, we look at about 30 to 40 properties of a material, and in any application we decide what properties we want, and accordingly we come across a set of materials that satisfy a requirement. In this course on classical thermodynamics, we are going to be concentrating on the thermodynamic property. So first, before we come to the properties, let's ask what is a pure substance and what are its general behavior. So pure substance is something we defined as something where there is the same molecule everywhere in the system. That means at any point, anywhere in the system, whether it's a flow system or a closed system, you say what is the molecule there, we say well it is this particular molecule and it is the same everywhere. So what we exclude by this definition are mixtures of surfaces or substances. So a mixture of say water and sand, or salt and water, or air and butane, we are excluding these. Technically, even air is a mixture, major components being oxygen, nitrogen, and then small quantities of carbon dioxide and other. So those would be classified as mixtures, but for the first analysis we will see how certain mixtures can be converted into a pseudo-pure substance whose properties are very easy to know, and that helps us in solving a lot of problems. So we will look at that later on. The pure substance itself can exist in many different phases. Okay, by that we mean that we can get properties which are varying now, and in all cases we can talk of property only when the substance is in equilibrium. So the phase that we are talking of is an equilibrium phase, and there we have three major categories: solid phase, liquid phase and vapor. So those are the three major phases that we have: solid, liquid and vapor. On this diagram I have shown something more where equilibrium state is possible. The word equilibrium is very important here. What it means is that we can have a situation where we have a liquid and vapor in equilibrium. We could have a situation where vapor and solid could exist in equilibrium. So in the first case we get liquid vapor mixtures. So these are now mixtures of a phase. So when we talk of mixture here in classical thermodynamics in this part, when we say mixture, we will mean it's a mixture of two phases. Later on, in the more advanced courses, we'll look at mixtures of pure substances. So we have liquid plus vapor mixture possible, solid plus vapor mixtures are possible, and solid plus liquid mixtures are possible, all individually in equilibrium. And yet one more is possible, where all three phases, solid, liquid and vapor, all three exist together in thermodynamic equilibrium. What that means is that when they are in equilibrium, which means that they are in thermodynamic equilibrium, it means that pressure everywhere is the same, temperature everywhere is the same, and species concentration, in our case it is only a one species, that is the same. So that means these mixtures satisfy this property, that everywhere in the mixture, whether you look at a small element in the liquid or a small element in the vapor, or in this case solid and vapor, or in this case in any of the three, in all cases the pressure will be the same, temperature will be the same, and of course it is the same species because we are looking at a pure substance. So if we say same molecule everywhere, essentially we are saying is the same species. So this is something new that is coming up, and it has a very far-reaching implication as far as a lot of applications go. So that's why we need to study this part. So let's look at a few examples where we see this. Okay, before that, let's look at what we know as the state postulate. The full details we will not go into it, but suffice to say that for our purpose, for a pure substance, a state is fully defined when two independent properties are known. Any two independent properties are known, which means that the pure substance, the state of that substance is fully defined. And that's what we will look at, that solving any problem, if we need to do some calculations based on the state, we always have to see, well, do I have two properties here? Are the two independent properties there? If not, do I have any more information in the problem by which I can get the properties that are not known? So there are two examples. This is the case of a cylinder in a piston arrangement, in which there is a piston there, and this is the working substance inside this. So we call this as our system boundary. It includes everything except the walls of the system. Now remember, this definition was very important, because if we said that my system is like this, then this boundary, which is the wall of the cylinder, is now part of the system. And when we talk of properties, we would have to talk of the properties of the substance inside here, as well as the substance here, and also maybe even any other substance over there. That makes life very complicated, and so we have to be very specific, as I have said all along, that we must define the system very carefully so that it includes the substance that is of interest to us and it is a pure substance. So this we call state 1, and if this comes down here, this is state 2. So in that case, the system boundary now becomes like this. So we know that this is a closed system, and we would apply the laws of the first law and second law of thermodynamics, and we'll say, look, what is the relation between the work, the heat, and the states, the state at 1 and the state 2. That means the properties at state 1 and 2. So if these three, any two are known, the third can be calculated. And that's what the entire exercise of problem solving in thermodynamics becomes. So that's what we need to know, that to get the states, we need the properties. And this information is important, because from this thing, we start doing the engineering of this device. For example, if in this process we know that this is the maximum pressure that the substance will take, we know what we can then design, what material should we have here, what material should be there for the cylinder, how thick should it be, how it should be made. All those decisions get taken based on these thermodynamic considerations. Then we have a second example of a flow system, that we have a tube through which a substance is flowing, and this is giving away its heat to the surroundings. Then there is a change in the property of this, and we want to know that what is the relation between the properties at the inlet and the exit state. And how is that related to heat transfer from this? So again, it's the same story that we first decide what are the of these things, what is independent and what is known, what is unknown, and then we calculate the unknown and then do the rest of the design. So like here also we get the same thing. If we know the state that it is going to be here, we say, look, this is the inlet pressure and temperature, this is the outlet pressure and temperature. We have to select a tube which will not rupture at the highest possible pressure or the temperature. And so let's see what materials we can take. What are those materials which are compatible with this substance, and now within that substance, how thick should it be, and all those decisions start to come in. So what I'm trying to say is that the basic thermodynamic calculation is the starting point for the entire mechanical design of the applications. So let's see a few pictures of these. Here is a picture of a ship that was launched this week for the Navy. And this ship has, if you read the details of it, it has got 4 gas turbines which propel this ship. We don't see those here, but inside there somewhere, you have 4 gas turbines which are taking in air. It burns the fuel, it generates power. That power drives the propeller of the ship. Like this, there are 4 of those. So that's another example I've given. Instead of the aircraft engine, a ship where the propulsion is done by a gas turbine. This is a photograph of a diesel generator set. So what you are seeing here is that this part is the diesel engine. Behind that is the generator which converts mechanical energy into electrical energy. This is the control panel, and in the front, this big square thing, this is the radiator which cools the hot water or hot coolant coming from the engine, cools it and sends it back. So if you want to do the thermodynamic analysis of an engine like this and predict, what is the power it will give, things like that, or what is the heat transfer rate in the radiator, then we assume that the working substance here is something. In this case, we assume that it is air. We treat air as a pure substance and start doing a set of calculations, and we get various numbers on it. This is a vapor compression system, the chiller of a central AC plant. So what this thing does is, right here in this part, there is a compressor which is operated by a motor. It's further behind this, we can't see that. It compresses the gas, sends it out into this big thing where you have water going through this, which condenses it, and this becomes a liquid refrigerant here. Then it comes down here, it is throttled, and here we have another set of pipes bringing warm water in, which gets cold and goes out as chilled water. This chilled water is piped to different floors in a building, over which then you blow air, and we get the air conditioning effect. This is at the heart of all central air conditioning plants. So how do we analyze this system? It is basically the same refrigeration system that we have seen earlier, except it's a much bigger scale, and everything is a lot bigger than what we see in a window AC or in a split AC. The last picture here is again something that we saw very recently. India launched a GSLV vehicle, and this is, you can see here, it's on the launch pad, just been ignited, and it's just now taking off. What you see here are on the side these 4 little things, which are strap-on boosters, which have a solid fuel which burns and comes out with a big, that gives a momentum there. And in the center are cryogenic engines. So this thing contains 2 big tanks, one having liquid oxygen, the other has liquid hydrogen. The 2 are pumped and allowed to burn. They produce a high temperature water which comes out and just gives thrust, and that pushes the spacecraft ahead. So we won't go into the analysis of this, where a solid fuel is being burnt, but the idea of what is hydrogen and oxygen, how do you get liquid hydrogen, liquid oxygen, why not gas, how does it burn, all those questions require the knowledge of thermodynamics that we are going to be looking at. And here we have a whole series of properties that I have listed. We have come across these. Pressure, temperature, and specific volume is something we came across right in the beginning. Specific volume is same as the reciprocal of density. So either we can say V or rho, that's okay. So these three somehow came very basic, which we got some idea of from school days also. Then we looked at the first law of thermodynamics and came up with these two properties: specific internal energy, specific enthalpy. Then from the second law analysis, we came across specific entropy. Now we'll define some more properties. One is specific heat at constant pressure. The other is specific heat at constant volume. And we'll briefly introduce two more properties. One is small g, which is called Gibbs energy, and small a, gives specific Gibbs energy, and the specific Helmholtz energy. So this will complete all the properties that we require. And the reason for introducing these two is that property relations, that the way they evolve, they actually start off from here in one sense, in a mathematical way, and give us equations by which we can calculate all of these. So that's the reason for introducing the Helmholtz energy. So A is called Helmholtz energy, Helmholtz free energy, or Helmholtz function, and you might have come across these in a course in physics or in chemistry. And G is the Gibbs energy or the Gibbs free energy. So these four properties, U, H, G, and A, all of which are energy, and specific energy is, we have been using kilojoules per kg. They all represent certain different types of properties of a substance or the properties of a reaction. For example, we know that H was U plus PV. That PV we now know is the flow work. Now, in a laboratory, we cannot measure all of these. This is a big problem. What we can measure is pressure, temperature, and we can independently measure mass and volume, from which we can get specific volume or the density. So those are only real world data that we have, from which we need to get the properties, all of these that we need for this analysis. So what we end up having is a set which is known as the PVT set or the P rho T set. And what we do is we try to fit a mathematical equation to this, and it is not a simple equation like polynomial or thing like that. It's a fairly complex equation. We try to make sure that it satisfies the property relations and Helmholtz equation, and then we differentiate it and do various operations on that to calculate U, H, S, and then you can even get Cp, Cv from there. After doing that, 50 years back, when computers and calculators were not there, all these properties were tabulated in a table. And a table cannot have continuous data for every pressure, every temperature. There were pressure, temperature data for very discrete points. And if one wanted to do a calculation with a property in between, one needed to do interpolation. Gradually that has given way, and now we have all these equations here programmed into a software package. You give a graphics user interface, and you can input two properties, and it will tell you all the other properties that you want. So we have reached that point. Some of these packages are available on the web also. Some others are there as open source, some are there with books. So if we use any of these, that's fine. It makes life a little more easier than using tables where you often have to do interpolation. So we have tables, we have software packages, and we also have graphs or charts or diagrams. Throughout we will try to depict every process on a property chart. So that helps us to quickly visualize what is the process and what is it that we are looking at. What is possible, what is not possible. Some very quick answers come out of that. These charts are nothing but taking all the data that we got from these property equations, and we plotted them with two axes, two axes, and the others as running parameters. We will look at those also. Okay, so this is how the whole big plan is, that how from these data, first how do we get this data? What do we understand about the behavior of the substance? And from this data, how can we get this data? Okay, so now we come to asking what is the thermodynamic behavior of a pure substance? And broadly, we can say that substances behave either as a gas or what I've put in quotes as a non-gas or not a gas. You can call it any of that. Within gases, we can say there could be ideal gas or a real gas. In non-gases, we of course include solids and liquids, because these are phases also that come in our discussions, and what we call as vapor. We do not call vapor as a gas, although quite often engineers do speak of a particular substance in a vapor state and they call it a gas. Sometimes it is justified, sometimes the error could be large if you assume it to be a gas. But we will continue with saying that it is a vapor and differentiated that under certain circumstances, this vapor can be treated as a gas, which in some situations can be treated as an ideal gas or else as a real gas. If a substance cannot be treated either as an ideal or a real gas, then we have to say that it is in this realm, either we call it the vapor states or the liquid vapor states, or just say that it is a non-gas behavior and we go back to our property data. The big difference here is that gases are very nice and easy to work with. An ideal gas is something you learnt in school. PV is equal to RT. The equation of state is very nice, very elegant, very simple. Real gases say, well, this is not the best thing. If you calculate the specific volume based on this equation and you actually see what is there in the real world, there could be a difference. That difference could be several percentage points, and that is not good enough. So we start making modifications to this equation, the simplest one being that we introduce the compressibility factor, Z, and then we get even more complex equations where we say that I will add many more terms to this equation to make it more and more realistic about the real gas behavior. So it is still not a vapor, but somewhat of a vapor in some cases, but not an ideal gas. The deviation from ideal gas is large. And so we do real gas analysis. We make this distinction, although I put these two as very different things, there is no hard and fast rule which says that this has to be treated as a gas, this has to be treated as a vapor. Liquids and solids obviously are not vapors or gases, so there is no issue of thinking about those as gases at all. The question then arises is which vapors can be considered to be a gas, and then which gas can be considered to be an ideal gas. This boundary as to where we make this differentiation, this we will come across maybe in tomorrow's lecture or a little later after that. But for the time being, let's say that there is no hard and fast rule. We say, look, if this number is met, then it is a gas. If it is not, if it is like that, then it is this. So there is a sort of a fuzzy boundary here, and sometimes we have to make our own judgment call in saying, well, okay, I'll accept so much uncertainty and I assume it to be a real gas. My analysis is going to be somewhat different than what I have here, but it's good enough to begin with. So this also we will see. What is the way by which we can say if a substance lies in this side or a substance lies in that side? A practical reason why we make this differentiation is that we can broadly classify most of our work to energy devices as gas-based devices or vapor cycle devices. A gas-based device means that the substance all throughout the cycle or the process is always a gas or an ideal gas. In this course, we will assume it to be an ideal gas. We won't worry about real gas. So we will stick with this. And examples are the spark ignition engine, the diesel engine, the gas turbines, aircraft engines, and quite a few other processes that we will say that this is an ideal gas. Now let's look at the analysis, apply the laws, and see how much work it produces, how much heat do I need to give. The analysis becomes very, very elegant and simple because the equation of state, PV equal to RT, is very nice to deal with. So life becomes very much more easier. But it is true only as long as the working substance is an ideal gas, which in our case we assume that it is air, which we assume to be an ideal gas, and so we can do all the analysis here. In more advanced analysis, we start relaxing the fact that air is not a pure substance, it's a mixture, it is not an ideal gas, let's start modeling it as a real gas, and then you start getting more and more the data that is in better agreement with what you see in practice. But in the beginning course, we do this. We take air as a pure substance, treat it as an ideal gas, and that gives us the handle to understand these devices. The behavior of vapor, and in many cases vapor plus liquid states, has applications like all steam power cycles. So coal-fired power plant, oil-fired power plants, nuclear power plants, all of which would account for like 80–90% of our electricity generation. There we come across a substance, in our case it is water, which is sometimes as a vapor, sometimes as a liquid. And we need to understand how do I get properties when it is vapor and what happens when it is a liquid. All our refrigeration systems, like the one I showed you just now also, that has some processes where we can treat it as a vapor, some processes where it is a mixture of liquid and vapor, and somewhere where it is only a liquid. So that's why this thing comes in. And an example that I gave was the cryogenic engine, liquid oxygen, liquid hydrogen. That is a liquid phase, but then it became a vapor phase and then burnt and it produced some thrust. So all these applications require us to understand the behavior of a substance when it is not an ideal gas. And that is where we will start our discussion today. Before that, let's quickly go through what you probably have learnt about an ideal gas in school days or in a physics course, and then we'll move on to the behavior of substance, vapor cell. So what we have as an ideal gas is that we assume that it consists of molecules which are considered to be a rigid sphere. Each one of them is a rigid sphere. They are moving randomly in space. Quite often they keep hitting each other, and we say that those collisions are elastic. That means it's like two rigid balls hitting each other. Momentum and energy get conserved. And as they keep moving around, we say that, look, this is called an ideal gas because the molecule will travel a certain distance. Say this one went here, this came here, and somewhere here they had a collision. And after that, this molecule went there and had a collision with another molecule over there, here. So this is a sort of a distance it was covering between two collisions. And if we know this distance for every collision that happens, and we take the average of that, that is called the mean free path. And the mean free path is much, much bigger than the size of the molecule, then we can quite happily say that this is a gas-like behavior. To put some numbers for you, diameter of a nucleus is of the order of 1.75 to 15, depending on the size of the nucleus, into 10 to the power minus 15 meters. The diameter of the molecule itself, including the electron cloud, is of the order of 10 to the power 10 meters, which means that if this is a nucleus, then the electron cloud occupies a space whose diameter is 10,000 times the diameter of this. And that's a huge space. And the next molecule, the closest that it will be, is one whose electron cloud touches this one. And when it touches, this could either be a solid or a liquid. This doesn't happen in a gas. These two are very far apart and they're hitting each other. So this gives you an idea about the typical sizes of the nucleus and the size of the atom. 10,000 is a number. The average distance traveled between two collisions in air at 1 bar and say 300 Kelvin is of the order of like 68 nanometers. So remember, this was of the order of 10 nanometers. This is 68 nanometers. So the mean free path is many, many times bigger than the size of the molecule. So that means that what we are saying here as a rigid molecule, there's a little nucleus in this. This is the cloud. This is the nucleus. This is the cloud. And the distance between them is much larger compared to their own diameters. 10 times, 100 times more. And as you go for greater and greater vacuums, this distance keeps increasing. If you look at a satellite orbiting at low altitudes, the distance between two molecules that you will see there is of the order of several kilometers. So that's at the low pressure side. At the high pressure side, as you start pressing these things together, these molecules all start coming closer to one another. The intermolecular distance becomes less, the distance between collisions becomes less, and gradually you start deviating from ideal gas behavior to a real gas behavior, and then finally it is not gas at all. So in liquids and solids, the spacing is of the order of 1 nanometer. In gases, it is 10, 100 times that distance. The difference is that in gases, these are all free molecules. They can roam around randomly where they want. In solids, they are vibrating about their mean position. And in liquids, they are slipping past one another and they take the shape of the material in which they are there, especially in a gravity environment. In a zero gravity environment, that property doesn't exist. Okay, so the ideal gas behavior starts to become a real gas behavior when the distance between two molecules has become such that gravitational attraction between them becomes significant, and it gets the molecules a little more closer than what we would have expected them to be. If they come even more closer, the nuclei begin to repel one another, and so the actual thing will be less dense than what the ideal gas equation will tell us. So these are what we have called the compressibility effects. We'll have a full discussion on this later on. For right now, I just introduced you to this fact that from an ideal gas, as we started compressing it or maybe reducing its temperature, these are all getting closer and closer. And at some point we say, look, I can treat it as a real gas by not using PV equal to RT, but using something else. And even after some time after that, we said, look, even using that is not good enough. There's too much error in it. Forget about it. It cannot be treated as an ideal gas. It cannot be treated as a real gas. And we start looking at the concept of vapors and liquids. I'll come back to the questions a little later because we will come to those questions in this module, certainly.